if I look out in the universe in no direction in particular, I would notice that on average, the universe looks very similar no matter where I look. So sure, there are stars and galaxies in some places and empty space in another. But if I zoom out and look at the universe in a really big, broad view, the universe does look pretty similar everywhere. So the universe still does tend to change with time. In the very earliest times, the material in the universe was very smooth, but over time, regions that had a bit more stuff in it were a bit heavier, so they had a bit stronger of a gravitational pull that would tend to attract more material towards them. So the denser regions got a bit more dense and the empty regions got a bit more empty as material was pulled elsewhere towards denser regions. But still, again, if I look at the universe in the biggest possible picture, the universe is very smooth and uniform everywhere. So a question we're going to ask is it possible to write the notion of a separation between events in space-time, where the universe can be the same at every location, but still evolve with time? And the answer to that is yes, we can. Here we have a line element, which is the ds square, the separation between locations in space-time, where the universe is the same everywhere. The left-right direction is identical to the up-down direction, which is identical to the in-out direction. But the universe is still allowed to evolve with time. So there still is a notion of a separation between locations in space-time that is the same everywhere, but not necessarily the same every when. So this term, a squared of t, this describes how the universe evolves in time. If a of t changes in some manner, then the separation between locations in space is going to change by following what a squared does. So mathematically, we would say a is a function of time. So what effect is having a separation between locations in space-time going to have on the evolution of the universe? So we said that the Einstein field equations are an intimate relationship between the shape of space-time, the separation between locations in space-time, and where all the stuff is in space-time. And then the matter in turn will move and somehow affect the shape of space-time and give space-time a new shape. And because space-time has a new shape, the matter will go somewhere, and now the matter went somewhere, and space-time will have a new shape. So in the context of what we're talking about, the manner in which the stuff that fills the universe dilutes is going to affect the way in which space-time evolves. And if space-time then evolves somehow, the matter that fills the universe will dilute somehow, and then that will affect how space-time evolves. And we have this cycle back and forth. So, if we want to know how the universe evolves with time, we're basically asking the question, what is the behavior of this function a? If a never changes, then the separation between locations in space-time will just be the same at all forever. But if a is something that's allowed to change, then means the separation between locations in the universe could change, and we could have some interesting behavior for the growth of the universe. So what we're going to do is we take the Einstein field equations and we take this ds squared, the term that describes the shape of space-time. We plug this ds squared into a few places. We go through some math. It looks very much like the cartoon over here. And then we find a term that contains all the curvature of space-time. So this g mu nu is going to tell how space-time how to curve. And so space-time will do what g mu nu says it should do. And then the material in space-time, the t mu nu, will react to that new shape of space-time. So t mu nu describes where everything is. It describes the stuff that is filling the universe. So essentially, T mu nu is going to be asking the question, how does the stuff that fill the universe dilute? So I want to take a moment to really think about, what do I mean by the word dilute? Let's imagine as a thought experiment that we live in a universe with 2 spatial dimensions and 1 time dimension. So we could move in the up-down direction, we could move in the left-right direction, but we move in time, but we don't have a third direction to move in. Now within this universe, I have 2 spatial and 1 time dimension. I look at this universe and I say, okay, let's say we have a box. This box is 4 light years by 4 light years on a side, and there is 1 chair inside the box. So I would say there is 1 chair every 16 square light years. 4 by 4 gives me 16. If I double the size of the box, then I would have a 8 by 8 box. So now instead of 1 chair in a 16 square light year box, I have 1 chair in a 64 square light year box, because 8 by 8 gives me 64. So I would say that if I double the side length of my box, all the chairs in my universe are going to dilute by a factor of 1/4. Now, let's ask, what would something like this look like if we live in a universe with 3 space and 1 time dimension? So let's say I have a universe, here are some galaxy clusters. I could count 1, 2, 3, 4, 5, 6 galaxy clusters. These galaxy clusters are in a cube of space that is 100 million light years by 100 million light years by 100 million light years. Now what I'm going to do is I'm going to double the side of this cube. So I go from 100 by 100 by 100 million light years to 200 by 200 by 200 million light years. Well, in this case, I doubled the side length of my cube. I went from 6 galaxy clusters every 10 to the 24 cubic light year to 6 galaxy clusters every 8 times 10 to the 24 light years. So if I live in a universe that has 3 spatial directions to move around in, I see that objects could dilute by a factor of 1/8. So the number of spatial dimensions in the universe will affect how things dilute. Now, this is just a thought experiment. We don't live in a universe that has 2 spatial dimensions. We live in a 3 plus 1 dimensional universe. But to ride on with this idea, different types of particles do dilute at different rates. So the photons, for example, and other particles that move really, really fast, they will dilute faster than slower moving objects like stars, clouds of gas and dust that are cold, galaxies, stuff like that. Now, another thing that affects the rate at which things dilute could be thought of as the number of spatial dimensions in the universe, the number of directions that you could possibly move around in. Now, if you notice on some of these words, I have this star for a caveat. Technically speaking, if I want to be fully accurate, the number of particles will dilute the same. What's really important to affect the T mu nu here is the manner in which energy density dilutes. So it's not important how the number of particles dilute, it's important how the energy density of particles dilutes. My goal for this course is to give you a good feel for how the universe behaves. I don't want you to really get bogged down by too many technical details. So you could think of this as though particles of light and other fast-moving objects dilute at a different rate than slow-moving objects. In actuality, it is their energy is what is important, and that's what we follow. How does their energy dilute? So, how does the space-time evolve? Well, we begin with this line element that we set up here. Let's, for the moment, assume that most of the stuff in the universe is stars and galaxies and other cold matter. So stars, galaxies, cold gas, cold dust, things that move much, much slower than the speed of light. And this is most of the stuff in the universe. This is the assumption that we're going with. So we will assume T mu nu behaves like it's mostly made up of cold, slow-moving matter. We have the ds squared here that we plugged into the g mu nu. We have something on that side. And when we crank through the mathematical machinery, g mu nu describes what space-time is doing. T mu nu describes what the stuff in the universe is. We find that there was a time in the past when the distance between every location in the universe was 0. And this time in the past we know as the Big Bang. So it's possible to actually trace backwards, and it turns out the number of years since then was 13.8 billion years. So there was a time in the past when the distance between every location in the universe was 0. So if you ever see a picture of the Big Bang that looks something like this, where you have a big explosion and things are flying out in every direction, this picture is absolutely wrong. The problem is this picture assumes that you can safely stand far away from the Big Bang and watch the birth of the universe. Well, if the distance between every location is 0, there's no such concept of standing far away and watching the Big Bang occur. A much more accurate description of the expansion of the universe is this picture on the left. So here, it looks like we have a lot of galaxies, and then we see the galaxies moving apart from each other. We're not falling downward. We're staying at the same distance away from this sheet of galaxies. The thing is, the sheet that holds that where all the galaxies are itself is expanding. And if we were to run this movie backwards, we would eventually have every galaxy in this picture be at the same location as every other galaxy in this picture. And that was the moment of the Big Bang.